Hello everyone, today we're going to be continuing looking at statics and equilibrium when dealing with horizontal planes and free space and also inclined planes. Now we're going to be looking at two examples from the Edexcel A-Level Maths Applied Book 2, specifically chapter 7.2 examples 3 and 4. Now in our last video we saw that when a system is in equilibrium and we're working with a horizontal plane or a particle in free space, we look at forces up and down and left and right. We say up is equal to down and left is equal to right. Whereas if we're dealing with an inclined plane, we look at the forces that are parallel and perpendicular to the slope. And we say forces up the slope equal forces down the slopes, and forces perpendicular into the slope are equal to forces perpendicular out of the slope. Now, on the left-hand side over here, I've got example 3 from 7.2. And it tells us that a particle is threaded through one light inextensible string and it's held in equilibrium. We need to find the tension in the string and the weight of the particle. So we're just going to put in our forces for this diagram. Now we will start with the weight because we know it's going to be going vertically downwards. Now you could put that as mg as well, but remember for weight we're just looking for w. If we're looking for the mass we would use mg. Now because this is being pulled downwards, there is tension in the string acting vertically upwards. Now, because this is being pulled actually downwards and to the left, there's also tension acting to the right as well to oppose that motion. Now, those tensions are the same value, but they're technically different forces. This force is a force going vertically upwards, and this force is another tension that's going to the right. Now, because they are created by the same string, this value of tension is the same as this value of tension. If they were two different strings, this would be T1 and this would be T2. But as we said, because it's one string and it's light and inextensible, it means the tension is constant throughout. Now, for this question, because this is a question we're looking at as being in free space, we need to resolve our forces into vertical and horizontal components. Now, I also need to add in our angle, which is given in the question, which is 30 degrees up here. Now, if we consider this diagram, if we look at the forces that are already going up and down and left and right, well, the W is already going up and the T is already going up and the W is going down, and the 8 newtons is acting to the left. That means the only force that needs resolving is the tension over here. We need to split this into horizontal and vertical components. Now, the tension is going to the top right, which means it's going upwards, and to the right. That means this force over here, which is adjacent to the angle, is going to be T cos 30, and this force over here is T sine 30. Now notice my diagram is very big to make this clearer for us, and when we're looking at this we can see that when we consider these forces we now split this T into a horizontal and vertical component, and the vertical component here is T sine 30. That means when we consider this question and we say that when we're looking at this up is equal to down, we can say that T is going up plus the T sine 30, because that is a separate force, is equal to W. Now sine 30 is equal to a half, so a half T plus T is 3 over 2T, which is equal to W. And we've now created an equation with two unknowns, which means there's going to be some form of potentially simultaneous equations. So now we need to consider the direction of left being equal to right. If we look at the forces going to the left, well, the only force to the left is the 8 newtons. The force to the right is the T cos 30. There are no other forces acting to the left or to the right. So here we have a question with only one unknown. Therefore, T is equal to 8 divided by cos 30, which is equal to a value of 9.24 or 9.238 newtons. So leave it as 9.238 newtons for now. And then once we've got our value of T, we can then identify the value of W by multiplying this value by 3 over 2. So we times that by 3 divided by 2, we get a value of 13.86 newtons is equal to W. So all we've done there is we've again resolved our forces into horizontal and vertical components that have been required, and then gone with up is equal to down and left is equal to right. The key thing for this question was though identifying that because it was one string that this is connected to, these tensions are the same value. If it had been two strings, it would have been two separate values for the tension. Okay, we now come to example 4 from chapter 7.2, and this time we're dealing with an inclined plane and also linking it to the topic of connected bodies and pulleys. First thing we're going to do is we're going to put in our forces and then resolve and then work out our values. Now the question is specifically asking for the value of P and the normal contact force and normal reaction force for the 3 kilogram particle up here. So we're told in this question that there is a particle over here which has a weight or is a mass of 3 kilograms, so there's a weight of 3g, and there's a 1 kilogram particle over here, so a weight of 1g. Now because this is a connected body and we're dealing with a pulley system, we do have tension acting on both particles always towards the pulley. So we've got those forces, and we also need our normal contact force over here, our normal force R, and that's all the forces put on the diagram. And just to finish up, then we need to make sure we resolve our forces by getting our angles in correctly. So I'm going to drop my perpendicular from over here. Our angle of 45 comes up to over here, and we have dropped our perpendicular and then make it become a parallel. So we have over here 3g cos 45, which is our adjacent, and then over here we have 3g sine 45. Now notice I've made a very large diagram because it's about making it clear for what we're doing. The other force I need to resolve is the force P. So P, I'm going to resolve, we need an angle, but we have an alternate angle here, a Z angle. An alternate angle meaning that 45 over here is also 45 over here. And if we drop our perpendicular from here, create a right angle like that, so that's going downwards, and that is going up the slope, meaning this is going to be P sine 45, and this is going to be P cos 45. And that is our full diagram, that is our full question effectively annotated. So for this, now because it's a connected body question and the system is in equilibrium, we're going to look at both these particles separately. Now normally for a pulley question we do F equals ma, but because this is in equilibrium, this particle is actually balanced, meaning that just from the right hand side, from this particle over here, we could say that T is equal to 1g, or it's equal to 9.8 newtons. So we actually have the value of tension for this case, meaning that this value of tension is also equal to 9.8. Now, because we're working with an inclined plane, we look at the forces parallel up the slope and down the slope, and then forces perpendicular to the slope. So I'm going to circle the forces that are parallel to the slope in black. So over here, parallel to slope, we've got our force T. We've got 3g sine 45. That's also parallel because that's perpendicular. That's perpendicular. And then P cos 45 is also parallel. P sine 45 is perpendicular. If we consider forces up the slope being equal to forces down the slope, we can say forces up the slope are P cos 45. We can say also up the slope is tension, that's also going up in that direction. And then down the slope is the 3g sine 45. Now that has two unknowns, but we know the value of T. We worked it out previously to be 9.8 over here. So we can say that P cos 45 is equal to 3g sine 45. 3 times 9.8 sine 45 minus 9.8 is equal to 10.99. And if we divide that by cos 45, we get a value for P equal to 15.54 newtons. We have our value for P. That was looking at the forces parallel to the slope. If we now consider the forces perpendicular to the slope, well, that is our R. I'll show some pink. So R, P sine 45, and 3G cos 45. Those are forces acting perpendicular. So if we say forces perpendicular out are equal to forces perpendicular in, we can say, well, R is going out, and then that is equal to 3G cos 45. And we are going to add on the P sine 45. Now, we worked out previously that P is simply 15.54. So if we multiply that by sine 45 and then add on the value of 3 times 9.8 cos 45, we get a value for R equal to 31.8 newtons. 31.8 newtons. And that is effectively the process. What we've seen here is, once again, when working with an inclined plane, you resolve your forces parallel and perpendicular to slope, draw a big diagram to make it clear. And because we said we're dealing with a connected body, we could identify that there were 3 unknowns here, P, R, and T, but we could obtain T from our second particle over here because the particle was in equilibrium, because it was a static particle. Anyway, I hope that's made sense. If it hasn't, please leave a comment below. Thank you very much for watching. Take care and goodbye.